process takes a very long time, on average 12 years for development of a successful drug of $2.6 billion. And much of this cost goes into drug optimization. So given a precursor, actually improving it for certain properties such as solubility, toxicity, or in our case, the propensity of the drug to actually target a protein of interest, and also in just surfacing these precursors in the first place. So the architecture that we were looking at first is a recent one proposed, which is essentially a semi-supervised approach to the generation or translation of drugs for a particular property. So you have an original data set of precursor molecules X, and then the Y's are basically just those molecules optimized for a certain property. You use it to train a generational model, which in our case is a variational autoencoder. And from sampling from that distribution by inputting given precursors and generating several outputs Y, you can actually use semi-supervision using an externally trained property predictor to filter out failing molecules and only allowing through certain ones that pass a threshold in terms of like property prediction. You add that back into an augmented data set and use it to retrain the generator, and what this does is it pushes it towards interesting chemical spaces that actually matter for the property. But as you'll see, this entire process is very dependent on property prediction, and in particular, property prediction for the propensity of a molecule to actually impact a protein is using very sparse data sets as of now. So CompBio, for example, a very popular drug-target interaction database used in this training process, has about 450,000 molecules and 1,300 targets, and only half of the targets have over 300 labels. So it's extremely sparse, and our hypothesis was that we could use protein-protein interactions to compute in a clever way on this data set, and then we could see how it impacts this downstream molecular generation task.
So prior to actually moving on to our protein-protein interaction-based method of imputation, we want to use a naive approach, which didn't include interactive information at all. And so for that, we used a matrix factorization approach on all drug-target interactions that were present in this CompBio database. Importantly, the database actually scrapes from the literature and then is later curated by experts. So we only included those targets which had corresponding small molecules that had been expertly curated, and we upper bounded our IC50 values at 100 to exclude very weak binders. When we did tenfold cross-validation following a single value decomposition approach, we found the errors pretty large, as you can see here by the RMSE and MAE values, but this is not unexpected given that our matrix was very sparse to begin with only 0.12% of the total possible interactions actually populated. So next we want to see whether including the protein-protein interactive information could actually improve our ability to impute these drug-target interaction scores. And so first we built a protein-protein interaction graph by leveraging a recent high-quality data set from this human reference interactome or theory. And basically what this is an all-by-all binary interaction data set where they do a series of these two hybrids assays between all proteins from all open reading frames of the human genome. And they actually found that the number of assays in which the interaction is detected validates to actually correspond to the strength of its interaction. And so we use this data set to generate an undirected graph and weight the edges by the number of assays in which interactions are covered. And when we first did some kind of high-level analysis on the graph, we were encouraged to find that the most largely connected aspect of this spanned almost the entire set of proteins, which is encouraging me that we can reach almost all the nodes through this interaction. But we want to also focus in our analysis into a subset of these. So we, for example, we want to target a particular tissue. And so we use GTEx data to filter down the interactome to only those proteins that were expressed in at least one brain tissue. And listed here are some of the most highly connected proteins by various metrics. These are encouraging heuristically because a lot of them represented proteins you expect to interact with other ones. Things involved in their ubiquitin proteasome pathway or involved in modifying other proteins to give some validation of the approach.
Cool. So taking that protein interactome, we kind of got to do our main contribution, which was extending a weighted random walk algorithm to the context of this interactome. So first we took our adjacency matrix from the PPI graph and used it to construct a probabilistic transition matrix. We also defined for each drug what we call the seed set S. So basically a set of proteins that had a non-zero normalized drug-target interaction score as derived from CompBio. And then we created these score vectors where all the non-seed set entries were set equal to 0, and the seed set entries were proportional to their interaction score. And then using the transition matrix, we iteratively applied it to this p vector until score convergence to perform this kind of weighted propagation, where the score that eventually ends up on each node is proportional to its likelihood of actually being interacted with through this random walk strategy. And we have this important hyperparameter beta, which lets us transition between local consistency, i.e. scores being similar for things that are nearby in the network, versus global consistency, i.e. the scores for the actually known seed proteins being correct. And so our results from this over tenfold cross-validation was that we outperformed the base model in RMSE, but did not outperform it in AE. And what we expected and what was kind of verified through our analyses was that random walk tends to be more conservative in its predictions, which means that it would generally tend to perform better in RMSE, which functions headliners more significantly.
At the beginning, Neil mentioned the presence of this external filter and the external property predictor. And so we want to see how the variety of these different imputation techniques would either improve or not improve our ability to generate molecules against specific targets using these external predictors. So we compared 3 different input sets into this filter. So one was one where we didn't have any augmentation imputation, so the base drug-target interaction matrix. The second was using this matrix factorization approach. And third was actually seeing whether using our protein-protein interaction could actually improve our ability to generate good binders for molecule interest, to target interest. And so for this, we used this PTP1B protein because it was the one that had the largest number of annotated drug-target interactions in our database. And we compared the success rate of our approaches. Unfortunately, most of the approaches performed quite poorly at about 0.1%. But we think this is driven by a couple of different possibilities. One, the actual predictor may not be optimized for this particular protein of interest. And two, given the sparsity of the data set that we began with, we might be overfitting the data. And this is something that we investigate in studies.
And in particular, we think that the most promising future direction, which kind of allows us to leverage a lot of our existing infrastructure for this, is basically in drug substructure motif finding. So in particular, if we have a target of interest, in theory, if we knew the relevant substructure motifs, we could then push the generator. So in other words, rules weighting, like by actually weighting the priors of the DAE or by changing the property predictor towards the chemical spaces. So suppose we have this protein of interest and we have a set of proteins that are nearby it, either in the PPI graph or even in alignment space. And then we have a set of drugs that interact over some certain threshold with this subgraph. We can essentially perform a variation of expectation maximization to detect the motifs that are interesting within the set of drugs. The major changes would just be that, first of all, for the locational vector Z, we might use a bidirectional smiles, or rather do the kind of finding the motif in embedded space to get rid of the fact that the orientation of the drug is arbitrary. And then in terms of the execution, the major changes would be that in estimating the PWM, we could weight it using drug-target interaction values for those drugs onto that subgraph. And then for validation, we would basically just try to find motifs that we know are important for these particular targets.
And we'd like to thank Manolis, Karas, and Misha, who received mentorship and support for this result, and also for the rest of the class.
So your hypothesis is that proteins that interact with each other are more likely to be targeted by the same drug?
Essentially that for a particular protein, we may be able to determine how the drug interacts with it based on its interactions with others that are close by.
Yes, but based on the interactions, it's very different from if they interact more or if they're in the same neighborhood, then they're more likely to be targeted by the same molecule.
Right.
So I think of it in a slightly different way. If two proteins have the same set of interactors,
as in the same set of drugs, yeah.
No. The same protein interactors.
Oh.
Then they're more likely to have a similar shape, and therefore they might bind the same drugs more often. So it's almost an orthogonal hypothesis. If A interacts with B, A is complementary to B. So you don't expect the molecules that target A to also target B, because the binding docking sites are actually complementary. It's A and not A, if you see. But instead, if you ask, how often do genes that, proteins that have a similar set of interactors also have a similar set of drug interactors?
Right, that's definitely different from our hypothesis, but that sounds pretty cool.
And in a way, your hypothesis also captures what I'm saying,
right? Because
by the random walk, if they interact with B, which they interact with C, I will also hit C.
Right.
So maybe the signal that you're getting is through the second round rather than the first round hops.
Right, it could be like flip-flopping.
Yeah, so it could be a 2-hop signal that's actually showing success. But if you directly look for only the 2-hop, not the 3-hop and the 4-hop,
Exactly.
you might actually get sort of more, and it just biologically.
Yeah, so that's kind of what we were also thinking with the potential future directions. We're actually comparing the proteins in some level of similarity, and we actually uncover motifs.
Exactly. So if you build a bipartite graph of molecules to protein, and you ask, you know, how does that bipartite graph compare to the set of interactors in the protein space?
Yeah, and I think that's something that ended up becoming more clear as we went on, was that this particular approach at the end would probably be more compelling to like alignment space proteins. Just to kind of line up.
Other questions? All right, great. Thanks again.